Okay, welcome to our next lecture here on polymers and the resulting bonding that exists between them, and ultimately how manufacturing is done with these unique molecular structures. So we've seen before that polymers may be fabricated or synthesized through their polymerization in a linear format, cross-linked, or even in a highly networked configuration. And even branching can occur depending on the chemistry and or the selection of materials or monomers used to make the polymer. So touching on the secondary bonding, revisiting this topic here in the context of polymers, we want to try to understand what forces might we expect between polymer chains as we consider building up a material ultimately that could be used for service roles like some of the utilities of plastics that we're familiar with. So we'll remind you that in polymers there are both primary and secondary bonds. Primary bonds in general are of course ionic, covalent, and metallic bonds. And in the case of the primary bonds found in polymers, we can expect primarily covalent, and in some rare cases, ionic bonding can play a role. Okay, the non-bonding interactions, also known as secondary bonds or van der Waals bonds, these can exist between molecules. These interactions are weaker than the primary bonds. Okay, so primary bonds are, again, the covalent bonds that hold the atoms together, and these secondary bonds are going to be weaker than those. But they can have a strong effect on the material properties because they're the only way that molecules in many ways can interact. Okay. So the strongest kind of secondary bond that we know of is the hydrogen bond. It's a non-bonding interaction, again, secondary bond. You can see here that the hydrogen bond is roughly 30 to 50 kilojoules for every mole of the bonds in question. And they form between molecules O, N, or F atoms, and between another molecule's hydrogen atoms where that hydrogen is bound to one of those same elements, O, N, or F. Okay, so perhaps the mnemonic or the memory tool to remember this is that hydrogen bonding is FON, where you need an FON element to interact with a hydrogen on another FON site on another molecule. Permanent dipole interactions can also form between molecules, and they have to have a polar covalent bond to help us here. We'll see an example of this in a moment, and some covalent bonds end up polarized because the bound electrons are more strongly attracted to one atom or another. That results in the permanent dipole, and then these dipole-dipole interactions can occur across molecules. Okay, and then there's of course induced dipole interactions, which are quite weak. These result from temporary dipoles that exist as two molecules get close to one another, and there's a fluctuation in the electron distribution across that molecule. Okay, so before we touch on thermoplastics, we'll just put some ideas into place for some of those secondary bonds that we just looked at. So in the case of, say, polyethylene, the carbon and the hydrogen bonds that exist throughout the polyethylene have relatively similar electronegativities, so we would expect no permanent dipole at the covalent bonds. Of course, carbon-carbon bonds are very much equally shared, given that the element is the exact same on the other side of that bond. So for polyethylene chains, cartooning this as a noodle and another noodle, the only way we could get interactions down the length of this chain would be through some van der Waal interactions that occur as there's fluctuations in the bond. So momentarily, there could be a temporary dipole established if the electrons in this 2-electron bond could shift to one side of the bond. So let's say, for example, briefly, the electrons here, which, as you may recall, are through an s orbital for the hydrogen and an sp3 orbital on the carbon. And so they largely exist like this. We could expect that momentarily that electron cloud, that density of electrons at bringing the carbon and the hydrogen together, may actually shift temporarily to put more electron density at a hydrogen. So in this brief moment, there would be a delta minus indicating more electron density towards the hydrogen and less electron density towards the carbon. And if there were another polyethylene nearby, there could be something similar where perhaps momentarily that polyethylene unit also had a shift in the electron density, perhaps this time positioning more electron cloud towards the carbon, and we would have a delta plus momentarily and a delta minus towards that carbon. So the opposite temporary charges here of the dipole show us a secondary interaction here, a secondary bond, and that is something we might expect in the polyethylene that does not have permanent dipoles or any elements available for hydrogen bonding. Okay. Considering hydrogen bonding next, let me just clean this up. So in the hydrogen bonding, we'll just look at, say, nylon 6,6 as an example. So we've seen that before. Essentially an NH, a chain of CH2s typically, and then an NH from the diamine component. We know that amide bonds exist in nylon. So here's our first amide bond that we've drawn with the NH next and bonded directly to this carbon-oxygen double bond feature. Okay, so this would be the repeat unit, the materials in the elements and the bonding within the repeat unit of nylon 6,6. And so we identify here at this point that we have a hydrogen bound to a nitrogen, and this suggests that hydrogen bonding could occur. So placing a nearby nylon molecule, we might expect that we could develop a hydrogen bond from one of the FON elements right here. Okay, so the lone pair of the oxygen could interact with the hydrogen atom to give us a secondary bond right here. And there's our hydrogen bond. Okay, and in the last case where we had a dipole-dipole bond, we'll show that quickly. For this, we'll use polyvinyl chloride as the example. So polyvinyl chloride, show a couple of repeats of that. There's a chlorine atom at every other carbon site. This continues on. because chlorine is more electronegative than carbon, we would expect permanent dipole to occur, where electrons are now directed more towards the chlorine than the carbon. So that is, there's not equal sharing, so there's unequal sharing in here. So unequal electron sharing. And that positions more of the electron towards the chlorine, and thus the delta minus that I've indicated next to that chlorine. And so we would see that at all chlorine side chains, and an opposite partial charge at the carbon center. So that's what I'm pointing to here. Okay, so if there were a neighboring polyvinyl chloride molecule, with delta plus at these carbon centers, we have now the opportunity between molecules to have some secondary bonds. So now we have delta minus, delta plus that is permanent and always there. And we have our secondary bonds this way. Okay, so these are the dipole-dipole interactions. Okay, so hopefully that has clarified some of the secondary bonds that we described on the previous slide. The three polymers that we've drawn to visualize those secondary bonds can all be grouped into the class of compounds called thermoplastics. And so a thermoplastic can be reversibly cooled and heated, and this lends to the concept for recycling or reusing the material. What happens is that when heated, it will soften. This will allow us to shape the material as desired or reshape it as desired, and then cool it down to set the form or the shape of the material. So for example, your polyethylene bags could be reprocessed with heating and then cooling with some sort of a mold to transform them from their bag format into some other polyethylene thermoplastic part or plastic material. Okay, so to contrast that now, in the case of thermosets, we are going to see that the material is not able to be recycled or reused. Instead, a thermoset, when heated, will form a molecular network via a chemical reaction. So let's put a visual to that. We'll go back a few slides. So a network looks like this, where at every repeat unit, there's extensive bridging and branching in all three directions, sometimes four directions, depending on the site for bonding, to extensively link every repeat unit to many neighboring units, not simply in a linear molecular fashion like we've seen in other examples.